Hello friends, in today's question, the displacement of the particles in a string stretched in x direction is represented y. Among the following expression for y, those describing wave motion are. So for the solution of this question, we are going to make use of the wave equation in the form of the partial differentiation or double partial differentiation. So we say the wave equation, which is given as partial derivative of y with respect to t, should be equal to or satisfying v square partial derivative of y with respect to x. Mind it, it is a double differentiation of in the form of the partial derivative. So whichever the equations are going to satisfy this relationship, those will be describing the wave motion. Okay. So let us start with our first option. So we say option A, there it is given that y of x comma t is equal to cos of kx and sine of omega t. So let us find out the first part, that is double derivative of y with respect to time. So the first derivative, partial y upon t, it will be equal to cos of kx multiplied by omega cos of omega t. And now its second derivative, y of t this will be equal to minus cos of kx omega square and sine of omega t. Similarly, we are going to solve for the second part, that is now with respect to x. So let us take the first derivative. This will be equal to minus of k sine of kx multiplied by sine of omega t. Now its double derivative, minus k square cos of kx, and here we have sine of omega t. Now substituting the equation, let us call this as equation number 1. So we can say from equation 1, we get minus of cos kx omega square sine of omega t v square, and here we have minus k square cos of kx multiplied by sine of omega t. And its solution, or we can say the simplification, it comes as omega square is equal to v square multiplied by k square. Okay. And which satisfy the if y is which is satisfied if omega is equal to vk. So you can say which is satisfied for omega is equal to vk. Therefore, it describes a standing wave, a wave equation. Therefore, it describes wave equation. That means option number A is a wave equation. Now, same thing we are going to do with option B also. Option B, it is given as y of x t is equal to k square, it is x square kx square minus omega square t square. And let us find out double derivative. First part, y of t square. This gives us, now it is simple calculation for each part. So we get this as y of t, which will be equal to minus 2 omega square t, and its double derivative t square will be equal to minus 2 omega square. Similarly, for second part with respect to x now. So we get first derivative with respect to x will be equal to 2k square x, and now its double derivative which will be coming as 2k square. Now once again using equation 1, from equation 1 we get minus 2 omega square is equal to omega square multiplied by 2k square, which gives us that omega square is equal to minus v square k square. Therefore, we also know that since omega, or rather we can say omega square, will be always greater than 0. Therefore, this equation is not satisfied. This equation is not satisfied. Not satisfied, the wave equation. The wave equation. Now we will go for the option number C. And in the option number C, we are given as cos square kx plus omega t. Option number C, we are given that y of xt is equal to cos square kx plus omega t. We can just modify using the trigonometric identity. We can write y of xt will be equal to 1 by 2 1 plus cos of twice kx plus omega t. Now here we are having two terms. One will be the constant part, that is our 1 by 2, and another will be the can say, trigonometric part. So we are only interested in this trigonometric part because the constant part is going to only add the, you can say, shifting of the equation. And moreover, as soon as we find out its derivative, a partial derivative, it will be negligible or vanishes. So we can just write that y of t has two components. Has two terms. First, a constant term which is equal to 1 by 2, and like I said, this contributes nothing to the wave equation since its derivative vanishes. So you can say this contributes nothing to the wave equation since its derivative vanishes. So we are only interested in the second term, and the second term is our 1 by 2 x of t is equal to 1 by 2 cos of 2 kx plus omega t. So we are interested in only this term, and we are going to find out its derivative first as well as second derivative. So the first derivative with respect to time t, this will be equal to 1 by 2, and we get this as minus sine of 2 kx plus omega t multiplied by 2 omega, and this can be further solved as 2 goes with 2, and this can be written as minus omega sine of 2 kx plus omega t. Now we write its second derivative is equal to, this comes as minus omega multiplied by 2 omega cos of 2 kx plus omega t, which gives us minus 2 omega square cos of 2 kx plus omega t. Now we solve it for x. This was our first part, and now we do it for with respect to x. Partial derivative with respect to x will be equal to 1 by 2 minus sine of 2 kx plus omega t and multiply by 2k, and once again 2 and 2 cancels out, so we can write this as minus of k sine of 2 kx plus omega t. Now taking its second derivative, we get this as minus k multiplied by 2k cos of 2kx plus omega t, and this comes as minus 2k square cos of 2kx plus omega t. Now once again we are going to use equation number 1. So we say from equation 1 we simply substitute the values. We get this as minus 2 omega square cos of 2kx plus omega t is equal to v square. Here also minus 2k square cos of twice kx plus omega t, and this gives us that our omega square is equal to v square multiplied by k square. And once again this equation is satisfied for omega is equal to v k. So you can say this equation is satisfied for omega is equal to vk. So it means this is a wave equation. This is a wave equation. Now we come to the part D, that is the last part. So we have option D, and here we are given that y of xt is equal to cos of k square x square minus omega square t square. So we are going to find out first derivative and second derivative with respect to time as well as with respect to displacement, that is x. So let us solve it for time. T will be equal to minus sine of k square x square minus omega square t square, and partial derivative of k square omega square minus omega square k square x square and omega square t square. Now k square x square is independent of t, therefore we can simplify it, and this can be written as equal to minus sine of k square x square minus omega square t square, and this will be coming as minus 2 omega square t, which can be further written as equal to, this will be equal to 2 omega square t, and we are left with sine of k square x square minus omega square t square. Now for the second derivative, so we can write this as y of t whole square, this will be equal to partial derivative of t, and this is about 2 omega square t sine of k square x square minus omega square t square. And we have two functions, both of them are dependent upon t, so we have to use a product rule in order to find out the partial differentiation. So this is a lengthy one, so you can write this as 2 omega square, you get this as sine of k square x square minus omega square t square plus 2 omega square multiplied by t, and this is our cos of k square x square minus omega square t square multiplied by minus of 2 omega square t. Minus of 2 omega square t. Which gives us, if you solve it, we can write it further. This will be equal to 2 omega square sine of k square x square minus omega square t square minus 4 omega raised to power 4 t raised to power 2 cos of k square x square minus omega square t square. This was our partial derivative with respect to time. Similarly, we are going to do partial derivative with respect to x. Partial derivative with respect to x. Once again, we can write that minus sine of k square x square minus omega square t square partial derivative with respect to x of the angular function, that is k square x square minus omega square t square, and this will be giving us minus sine of k square x square minus omega square t square multiplied by two k square x square. So we get the partial derivative will be equal to minus 2k square x square sine of k square x square minus omega square t square. Now once again the double partial derivative, and once again we are going to make use of the chain rule or product rule, that is equal to x square. So let me write the result for this directly, and it will save a little bit of time. This comes as minus 2 k square sine of k square x square minus omega square t square minus 4 k raised to power 4 x raised to power square cos of k square x square minus omega square t square. Now we are going to use equation number 1. You can say from equation 1, we simply substitute the left hand side as well as the right hand side. Okay, so we can write this as 2 omega square sine of k square x square minus omega square t square minus 4 omega 4 t square cos of k square x square minus omega square t square will be equal to, and we are left with here v square and to omega square not omega square but k square minus 2 k square sine of k square x minus omega square t square, and this is minus 4 k raised power 4 x raised power 2 cos of k square x square minus omega square t square. And if we equate the terms, we can clearly see for the sinusoidal function on the both sides. Okay, so let me say here that for sine of k square x square minus omega square t square, we can write that our 2 omega square minus 2 v square k square. Once again, because this is same as omega square will be greater than 0, so this particular equation will not be your wave equation, okay? Because we have already proved it. So you can say this is not a wave equation. And similarly, if we make a comparison between the cosine terms on the both the part, in the cosine terms, especially the angular function, which is the square, the terms indicating t square and x square do not match. Okay. So we can say for cos, we have here k square x square minus omega square t square. The terms involving t square and x square do not match. So therefore, not a wave equation. Not a wave equation. So we have only two, that is our part C is a wave equation, as well as we have part A is also a wave equation. So A and C are the correct options. Okay, so we are left with that option A and option C are the correct ones. So we can say option A and C are the correct. Option A and C are the correct. No doubt this question was easy but a lengthy one, because we have to find out the partial derivative twice and of every function, especially the last part. So this completes the question. Thank you.